Hello and welcome to the homework help video for the Unit 7 practice assessment. We're going to start with part A, and this part deals with the definitions of logarithms and as well as the three forms of expressions with exponents. So of course we have our standard exponential form, some base to some power equals, well, some value, some result. I'll call it the result. I like that. Radical form just changes a little bit. If you know the power and you know what the result is, your answer will be the base. It's basically, I have this many of something being multiplied together, and that's what I'm going to get as a result. What is it that I'm multiplying? That's what radical form tells us. And then logarithmic form gives us that last thing. We've had C and B as answers. The logarithmic form just says, well, if I have a base of whatever, how many of them am I multiplying to get this result? Cool. So looking at number one, we have logarithmic form. It's obvious because it says log in there. Amazing. So we see that the base is 8. The result, the answer, the value, whatever you want to call it, is 512. And therefore, the exponent, which I'm calling A, whatever, that is 3. So if I'm going to put this into exponential form, I want the base and the exponent, and put those on the left-hand side, and then that C, the result, whatever you want to call it, put on the right-hand side. So that is exponential form. And of course, radical form, well, just takes that exponent and the result there and puts it on the left-hand side, and then the base is on the right-hand side. And those are the two other forms. So that's exponential and radical form using that same information that the logarithm gives us. So let's do 2 and 3, hopefully more quickly. Let's see, we got a base of 9 here. We have the result of the exponential form is 81, and then we know the exponent is 2. So that's because, by the way, if you don't see a number in there, there's a hidden 2, square root. So we can write this as 9 to the power of 2 equals 81. And we can also write this as, what do we need, the logarithmic form? Well, this is going to be log, let's see, log base 9 of 81 equals 2. I think that looks good to me. Number 3, we know the base, and we know is 5. We know the exponent is 4, and we know the result of that is 625. So logarithmic form uses the same base, of course, and switches the exponent and the result there. I need 4 5s multiplied together to get 625. Easy. And radical form, of course, we're going to take that exponent. I know I have 4 of something. I am multiplying them together to get 625. That something is, of course, 5. Okay, cool. So that's that. We move on to number 4. In number 4, we just have to know how to evaluate these things. And again, we already mentioned that the answer to a logarithm is an exponent. So we have 2 to some exponent is going to be equal to 128. I just have to figure out what that exponent actually is. And I could just start multiplying 2's if I wanted. In fact, let me go ahead and bring up a calculator. And there it is. And let's just start multiplying 2's. 2 times 2 is 4, of course. Another 2. This is going to be 2 to the power of 3. That's 8. 2 to the power of 4 is 16. Then we have 32 for 2 to the power of 5, 2 to the power of 6, and 2 to the power of 7. So that's our answer. Our answer to the logarithm is 7 because 2 to the power of 7 is 128. Awesome. There is another way that you could do this. I will get back to that as soon as we talk about number 7. Number 5, oh no, I'm sorry, not number 7. There's another problem later on where we have to use the change of base formula. I will refer back to number 4 at that point. Number 5, evaluate this expression. Well, again, we have a base to some unknown exponent, and that's going to be equal to 4. Now, this can seem like a strange question until we remember that we can use exponents in ways that, well, they're just different. Instead of saying how many of this am I going to multiply to get this, well, you can't really say that because the answer is less than the number that I'm multiplying. But then we remember that fractional exponents mean things like roots. And in fact, 4 just happens to be the exact square root of 16. And that's going to be our answer, is that this is the square root of 16 is 4. And a square root can be written as a 1/2. I'm not sure I left myself enough space to write a fraction. So let me erase that and just write in 1/2, because the square root of 16 is 4, so 16 to the power 1/2 is 4. And our answer is 1/2 because, once again, the answer to a logarithm is an exponent. Number 6, evaluate this expression. ln of 1 is 0 because all logs of 1 are 0, unless it's log base 1, in which case that's undefined. We'll talk about that on number 9. And the reason is, again, it's some base. In this case, ln means log base e. So we have log base e of 1. And the reason that equals 0 is because it is e to the power of 0 equals 1. And that's because anything to the power of 0 equals 1. The only maybe exception to that would be 0 to the power of 0. But even that, if you had to give it an answer, you would say 0 to the power of 0 is 1. You'll have to learn about fancier words, things like limits and blah, 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 to understand why. But yeah, everything to the power of 0 is 1. And so, yeah, the power of 0, the answer to a logarithm, he said for the 3rd or 5th or 10th time, is an exponent. And so the power is 0, so the log of 1 is 0. Cool. Evaluate the expression log 50. There is no tricks to this one. You just type in your calculator. Oh, I got to clear it first. Log 50. Now this is the computer calculator. So this one works a little bit differently. You have to type 50 first and then press log. But in your handheld calculators, you type log and then you type 50 and then you get this answer, 1.69, and we'll just call it 9. 1.699. Of course, note that I did put the approximately equal, well, I tried to, my squiggly line looked a little weird, but that's okay. And it's because I did some rounding, right? All right, on number 8, why does this expression have an undefined value, log 0? And let's, again, define what's happening here. Log without a name, wait, what? Log without a stated base is base 10. And so this is 10 to some exponent that equals 0. And that's impossible because exponents mean that you are multiplying by some number, right? So there's no number of 10s that I can multiply to get 0. It means also that you could be doing some type of root. How many, if it was like a square root, for instance, it would be, oh, I have 2 of these numbers that multiply to get 10. Well, clearly that's not 0. In fact, no matter how many of any number I have that multiplied together, that will never be 0. 0 will never be that base because 0 times 0 times 0, that's never ever going to be 10. So that the roots are out. You could also argue, what about a negative exponent? That gets closer, you're getting warmer, but then a negative exponent just means instead of multiplying, you are dividing by more and more and more and more and more of these 10s. I don't care how many 10s you divide by, it's never really gonna be 0. You have to do it by an infinite amount of them. And since infinity is not an actual number, we would say that the log of 0 is undefined due to the fact that it doesn't matter how many 10s, in this case 10s, you divide by, you are never going to get 0 as a value because, again, it's 1 divided by some number, and that's going to be a number, not 0. So that's why number 8 is undefined. Number 9, again, I'll turn this into exponential form to show why. 1 to what power equals 9? Well, I don't care how many ones you're multiplying or dividing or rooting or whatever. Together, you're always going to get 1. You're never going to get 9. And that's pretty much that. That's why. So hopefully that makes sense. And let's move on to the next section. Welcome back to part B. And in this section, we are solving equations. So I just put some reminders at the top. If you have a logarithm and a base with the same, a logarithm and like an exponential expression with the same base, then they will cancel each other. So ln, for instance, is log base e, and we have a base of e in the exponential thing as well, and they cancel. We have a base of 4 with an exponent of log base 4, and so those cancel. And it works the other way as well. We have 10 to the power of x. We have that base of 10. Log, without anything else stated, it's not log base 2 or anything like that. That's also a base of 10, so that cancels. And in each of these cases, you're just left with whatever that is. So in the simple version for each of these, it's just x, but it doesn't have to just be x. It could be anything. However, do note that in order for this to work, you do really kind of need to have your logarithm isolated. There are some exceptions if you are creative with the log rules. For instance, on number 1, I could bring that multiplication of 2 up top and call that a power of 2 in this expression inside the parentheses. However, it's also perfectly fine to just divide by 2 to isolate that logarithm. Of course, don't fall victim to the trap saying 0 divided by 2 is undefined. That would be 2 divided by 0. And from here, all we got to do is cancel that log with this trick that we see up top. And we're going to use 7 to the power of the left-hand side and 7 to the power of the right-hand side. Maybe I should have given myself more space. That's okay. We'll make do. And on this one, we see, all right, the 7 and log base 7 cancels. We end up with negative 2x equals, well, 7 to the power of 0 is the same as everything to the power of 0, and that is 1. Yep, I'm going to go ahead and give myself a bit more space here with the magic of technology. All right, we'll come back to those problems in a minute. And then I'm going to divide by negative 2, and that's going to be my answer. X is negative 1/2. Cool. Number 11. Again, I want to isolate this logarithm first. I have this constant that I would like to cancel. I do like to cancel constant values first. However, I can't do that because it's in the parentheses, and the parentheses are there because of the logarithm. I got to get rid of the logarithm first. However, that constant is absolutely not protected by those parentheses. So that's what I'm going to get rid of first. And I'm going to end up with 0 on the right-hand side. Now I can cancel the logarithm since the base is not stated. This is base 10. And then I can subtract 3 to get my answer of negative 2. Number 12. I once again need to isolate this logarithm, so no big deal, just like I did in the last one. And now to access that variable there, I need to cancel this log base 5. So my handwriting was not that good here. So this is 5 to the power of log base 5 of negative m, and that equals 5 squared. Cancel, and we end up with negative m equals 5 squared, which is 25. And divide by negative 1 or multiply by negative 1. Get m equals negative 25. And that's my result. Let me scroll down. And let's get rid of this bottom bar. I got a feeling I'm going to need more space than that. Isn't technology wonderful? All right, so number 13. This one could throw you for a loop at first. However, you got to remember that these are both the same function. So if the same function is happening to two different things and yet they're equivalent, then they aren't different things, they're the same, and you can just set them equal to each other, completely ignoring the ln. However, if you wanted to cancel that ln, you would just say e to this power, e to that power, and that's because ln is, once again, as stated at the top of this section, it's log base e. So there you go. Either way, you end up with 5x equals 2x plus 9. I find that advanced students, sometimes the easiest problems, they think, well, they've learned so much that they think something's complicated is supposed to be happening, but no, it's not. Don't overthink it. You're getting all the x's onto the left-hand side, and then you're moving any constants and or coefficients onto the right-hand side. There are no more constants on the left-hand side, or rather, there never were, and that's where the variables are, so I just got to get rid of the coefficient, and I end up with x equals 3. Moving on to number 14, once again, there's the log, there's a bunch of stuff inside of it, but I got to get rid of that negative 6. No, do not add 6. That is negative 6 times log. I hope I don't have to go over that too much. So let's divide by negative 6 and divide by negative 6, and we're going to end up with log base 3 of r minus 2 equals 4. Let's go ahead and do 3 to this power and 3 to that power. Those cancel, and I get r minus 2 equals 3 to the power of 4. 3 times 3 is 9, times 3 again is 27, times 3 again is 81, add 2, and I get my answer. R is 83. Last but not least, number 15. This one could, again, throw you for a bit of a loop, give you a few problems until you remember that we learned these things called the log properties, and this is an addition. Addition of two logs with the same base means that you can put them together and multiply whatever is in both of those logarithms. So I have log of 2x, and again, this is log base 10, and that equals 1. I don't like this equal sign, and I'm picky. Cool. And to cancel the log base 10, I'm going to use a base of 10. So there it is. That cancels 10 to the power of 1 is 10, and I end up with, of course, 5 as my answer. So that's section B, or part B, whatever I called it. Moving on to the next part. On to part C, properties of logarithms. Just a few questions in here. I didn't want to stress this too much. And, well, we have just a few properties to work with. We have, when you are multiplying something in that logarithm, then you can separate it with a plus instead. We've already talked about this one. If it's a division instead of a multiplication, you can switch that to a minus. If what you're finding the log of has an exponent, you can bring that exponent down in front. And then finally, of course, we have the change of base property, which I said I'd talk about number 4 again, and here's where it is. That was log base 2 of 128. So I could have said log of 128 divided by log of 2 and put that into the calculator, and that would have given me my answer, and that would have been totally fine. However, might as well have talked about the other way of finding logarithms. Is just that that's not always possible. So for instance, skipping to number 18, just because I'm talking about that, change of base rule, how many 3's do you have to multiply to get 7? Well, it's not 1 and it's not 2. 1's too small, 2's too many, and therefore it's something in between. We need to use change of base. I've mentioned this several times, just in case somebody needs a reminder. It doesn't necessarily say that it has to be log base 10. It's just that oftentimes we use log change of base formulas because we're trying to actually calculate it, because there is no log base 3 button in most handheld calculators. And so that's why usually I just say log 7 and log 3, but really it could be log anything. It could be log base 12 of 7 and log base 12 of 3 if you wanted it to be. I don't know why you would, but you could, as long as they match top and bottom. Another thing you could say is ln. Sure, why not? That's log base e. That works. And the nice thing about that is there's an ln button on the calculator. So these would both work. if you were just trying to calculate the answer, totally does not matter. All that matters is that you actually, type it into the calculator correctly. So I'm going to clear this. Again, on the handheld calculator, you would actually say log 7, whatever, divided by log 3, and that's how you get your answer. But since this is a computer calculator, I'm using that to type 7 and then press log, and notice it says log 7 up here. And then I'm going to say divided by 3, but not 3, it's the log of that, and that's log of 3, and press enter, and I get log 7 divided by log 3 is approximately 1.771, and that makes sense because I said 3 was too few. 3 to the power of 1 is only 3, I'm trying to get to 7. 2 3s is too many. 3 to the power of 2 is 9. That's too big, so this is the power, approximately. Again, it's rounded, as, of course, most of these things have to be. I can't write infinitely many digits. So I typically will round to 3 decimal points, and I'll call it 1.771. And since I am rounding, I guess I should use the approximately equal sign. And if I remember, it was 1.771. Yeah, okay, just double checking. Moving backwards, I guess, to number 16. This one was interesting because you had to use, and again, that's what makes math so hard, is you have to use a combination of rules for so many of these types of problems. The rule that I'm using here, of course, is that a radical, a root, can be written as a power, and in this case, this is going to be log base 4 of x to the power of 1/2. And using this property, we can say, well, powers can be brought in front, and so this is going to be 1/2 the log base 4 of x. Cool. And that's it. Number 17, that one, well, we get some more interest here. One of the things I can do is bring down this 2, and one way to look at it is that this x to the power of 3, that has a power of 2, and 4, that has a power of 2. Cool. And so I'm going to go ahead and bring this down in front now, and then later on I'm going to be splitting it up because we see we can use the division rule here. So the thing to remember here is that both the numerator and the denominator will have a 2 in front of them because both of them have this same power. That's what it means to, I believe this one's called the power of quotients property. Those get confusing. There's quotient of power and there's quotient of powers and there's powers of quotient. There's so many properties. It's crazy. Anyways, I'm probably rambling too much. Let's just keep going. Cool. And once again, I am going to kind of break this one down and call this. I'm sure I'm putting this, me working at 3 times or maybe even 4 times speed, but if you caught it, I actually forgot to put the 2 at first, and this is a very, very common mistake. And I was just talking about how both of these should have a power of 2, so both of them should have a coefficient of 2 in front. So yeah, don't forget. It's easy to forget. I forgot. So, and that was immediately after me talking about it, so it's very, very easy to forget that. We would be done, except this x, it still has a power of 3, and powers can be brought in front. And since it's going to be a multiplication, yeah, it's going to be 2 times 3, and that gives us final answer 6 ln of x minus 2 ln of 4. And there you go. That's our answer. Right. Moving on. On part B, we are asked to graph, and we have a handy transformation function we can use. A times log base b of x minus h all plus k. One thing to note about this is that just due to time constraints and whatever, we are going to, you're not going to be given one with an a value. Alas, there's only so much we can fit into a year. No big deal. So we're mostly focused on h and k and just general shape of what these things look like. And let's look at the reference points. The reference points for any logarithmic function are at 1, 0, and b comma 1, where b is just the base. So when I look at number 19, it's going to have a reference point at 1, 0, and it's going to have a reference point at 4, 1. And again, that's just because, remember, the answer, in other words, the y value of a logarithmic function is an exponent. And so all this is saying is that what exponent gives me, 1, if I input 1 into the logarithm, well, yeah, everything to the power of 0 is 1. That's why it's 1 comma 0. The power is 0, the answer is 0, therefore the exponent is 0. Anything to the power of 0 is 1. Anything to the power of 1 is itself, and that's why it's going to be at b comma 1, the base. Yeah, there you go. So that's it. Those are the parent function points. And likewise on number 20, we can go ahead and put those reference points in. This time it's base 6. So there are our reference points. And cool, let's get our h and k values. So here we have h of 2, and on the other one we got an h of -3, careful. So I'm going to move both of my reference points right 2 on number 19 and left 3 on number 20. So there they are now, the points are in red. And, I guess I should do that for number 20. One other thing moves left and right, and that is the vertical asymptote. So normally it is on the y-axis. However, it also moves left or right, just like the points do, and so it's going to move right 2 for number 19 and left 3 for number 20. And notice that it's still 1 away from the first reference point there. Cool. And of course, last but not least, we have our k value. So in number 19, that is going to be a shift up 1. And in number 20, that is going to be a shift up 2. And there they are. All we need to know now is, well, the graph of this thing is going to basically hug, for lack of a better word, the vertical asymptote until it gets pretty darn close. And my hand was wiggling a little bit, so I went into the wrong side of the horizontal. I keep calling it horizontal, vertical asymptote, but it should be basically right on that vertical asymptote until it gets pretty darn close to the first reference point. It hooks a right, goes through the second vertical. I'm getting my names mixed up. It goes to the second reference point, and there you go. Likewise, it hugs that vertical asymptote pretty closely. If I wanted more, perfection, I would turn myself into a robot. That does it. That's pretty good for a sketch, though. And so there you go. That's how to graph them. No big deal. Easy. On to section E. And yeah, I think this section should be nice and short because we really only have this one definition here. In fact, the only reason we included this into the logarithmic unit was because that, well, sometimes the answers to logarithms are exponents. Wait, what? Always the answers to logarithms are exponents, but sometimes those answers are fractions. That's what I meant to say. Words are hard. So looking at number 21, we have a base of 4 and we have a power of 3/4. Well, the denominator is going to turn into a root. So this will be the 4th root of 4, and that's all going to be to the power of 3. Now, I would have to double check, is this something that I can actually, simplify a bit? And no, because what number, if I have 4 of them and multiply them together, I get 4? The answer is not 1. This is multiplication. So there is no number, no nice number, as I like to call them. And so therefore, I would have to approximate the decimal in order to write out, to write this not in radical form, to write this in like a single number. And so therefore, I'm not going to do that. Besides, the instructions say write in radical form, so I've done that. Sweet. Moving on, number 22. This one is in radical form, wants to write it in exponential form. Thing to remember about this one is, well, the root is the same as the denominator, but we don't see a root, and therefore that number is, of course, 2. If you don't see a number in the root, it is a square root, and therefore it's a 2. So that means that I can go ahead and call this 8 to the power of 5/2. And that's the exponential form of it. Done. Number 23, simplify this. So normally when it says simplify, then not guaranteed, but a lot of times you will be able to turn this into like a single number or something like that. And we will, because this is going to be 343. I want to cube root that and then square all that. Order matters. 3 is the denominator, so 3 is the root. And yeah, this one does have an answer. The cube root of 343 is 7, because 7 times 7 times 7 is 343. Again, you got to remember the question these are asking. I got 3 of a number, and I'm multiplying them all together to get that. So that is 7. And 7 squared is 49. And there you go. That's this section done. Moving on to the last one. Welcome to the last section. I had a feeling I need more space, so I went ahead and spaced out these problems. And we are finding inverses. Cool. And again, this is another one where it's not really, finding inverse functions is not specific to logarithms. It's just that this is where we brought it up. So therefore, I'm including it in this section. Cool. And inverses, again, it's just what steps do you have to take to solve this equation? For instance, if this was 5 equals 4x minus 1, well, in order to solve this one, I'd add 1, and then I'd divide by 4, right? So that's how to solve this equation if I plug in something for f of x, if I plug in some y value, right? And inverse function is only asking, well, what if I wanted to solve for any given y value? That's what the input is for the inverse, and it'll get you an answer, right? It'll get you the output of the inverse function. The y value of the inverse function is what x value you'd have to plug in to the original function to get that value, to get that y value that you plugged into the inverse. So a lot of, back and forths, swapping x's and y's, and it can be confusing, absolutely. So a lot of folks find this easier if you just call f of x y, and this is not needed. You can totally just swap as is and call it f inverse from the beginning. It's just some people find this easier, so I'm going to mention that, and I'm going to go ahead and swap their locations. And now the process says solve for y. Yeah, no big deal. If I want to isolate y, that means I need to get rid of the 4 and I need to get rid of the minus 1. So let's do that. This is a coefficient and that is a constant. And just like anytime you're solving for a variable, you get rid of constant values first, and then you get rid of coefficients. Do note the rules for multiplication and division say everything on that side you need to multiply or divide. So it's the entire x minus 1 expression that you want to divide by 4. So all of that, both x and 1 should both be in the numerator. And I'm going to go ahead and switch this back to f inverse because it was given in function notation. I will give my answer in function notation and go ahead and say that this is x plus 1 over 4. That's the inverse function. Cool. And again, just the idea of inverse function. If I said that I was looking for, well, how about, let's do one that works nicely. Let's say 7. If I was plugging in 7 into the original function for y, if I was looking for a y value of 7, what x value would I have to plug in? Well, in this case, you'd plug in 7 to the x value of the inverse. Again, there's that idea of swapping places. And 7 plus 1 is 8, divided by 4 is 2. And so the answer, the y value for the inverse, is 2. That means 2 is the value that you should plug into x in the original. So that's all we're doing. So moving on to number 25. Let's go ahead and finish this thing up. Just to show you that, again, you can swap. You don't have to. By swap, I mean turn f, g, h, whatever into y. You just totally just leave it as g of x, and that's fine. However, just be a little careful with the notation. I would say, all right, here's 5 times, and then we have g inverse of x. Totally fine to write it like that. And then we're going to go ahead and square. And, as long as you know that this is the thing that we're solving for, then you don't get confused by this -1. It's totally fine to write it like this. And let's see, I want to get rid of this square, but in order to do so, I think I'm going to have to isolate that square. So let me go ahead and divide by 5. And again, I typically will do my divisions of 5 or division of anything like this, but really it is the entire right-hand side that's being divided. Why do these things not get divided? Well, again, it's 5 times this whole thing. Like, that's all in parentheses. It's 5 times all that junk. And so multiplying by 5 and dividing by 5 cancels it, and it's not going to affect all the other stuff in there because it's in parentheses. Cool. And so I get x over 5 on the left-hand side. Whenever you get rid of something that could remove parentheses, it's always important to remind yourself, to ask yourself, really, did I remove those parentheses? And in this case, no, because there's still another operation, the square, that would necessitate those parentheses to still be there. So I need to get rid of that square. You cancel exponents with roots. It's really difficult to keep track of every single rule, every single opposite, blah, blah, blah. Sometimes people are going to want to use log base 2 here, but logarithms cancel bases. They leave you with the exponent. The answer is an exponent. If you want to cancel the exponent, you use a root. In this case, it's going to be a square root because it's a square. And yeah, don't make fun of my squiggly lines. I can't draw straight lines. I'm sorry. Anyways, moving on, we get the square root of x over 5. I was going to say plus 5. Silly me. Now we can remove those parentheses and end this problem by subtracting 3. Do note this minus 3. It's not going to be 5 minus 3. That 5 is 1 in the denominator and 2 in the square root. It is double protected. It's just not a like term there. But we can go ahead and say that this inverse, whoops, forgot the negative 1, is going to be the square root of x over 5 minus 3, and do make sure that minus 3 is outside of the radical. Moving on to number 26, we have a root of 3. And again, if a square root cancels a power of 2, a cube root will be canceled by a cube. No big deal. You can also think of this as a power of 1/3, and therefore 1/3 times 3. That cancels. But I am getting ahead of myself because we do need to go ahead and swap locations anyways. First, hey, that was a pretty straight line. I'm pretty happy with that. And again, I'm going to cube both sides. And the root and the exponent cancel. We get x cubed equals. And now I have a coefficient and a constant. Of course, remove the constant first. And then the coefficient. And that's our inverse function, x cubed minus 1 all over 2. All right, let's finish this off. We have 27 through 29. And number 27 starts off with one that could be, daunting, I suppose, because it has E in there. And our understanding of E, it's starting there, but perhaps we're not experts in the idea yet. But, no big deal. We got this. So all we got to remember is that this is a base, and bases are canceled with logarithms. Remember, that's what I was talking about in those previous couple of problems, is that there we were canceling exponents. Here we want the exponent. We're trying to cancel the base. So we are going to use log base e to cancel that e, otherwise known as a natural logarithm, or ln for short. However, once again, I'm getting ahead of myself. We got to swap locations here. All right, now we can go ahead and say this is ln of x equals ln and e cancel, and we end up with the inverse function plus 3. Let's go ahead and remove that plus 3 with a minus 3, and we get our answer. The inverse is ln of x minus 3. Done. Number 28. All right, this time we have a logarithm, and if a logarithm cancels a base of e, A base of 10 will cancel a log base 10. Let's go ahead and do our thing. You know what? I think for this one, I'm going to go ahead and call this y. Because why not? Just to remind you that you can do it. And we are going to isolate the logarithm first, divide by 2. Do note you could put the 2 over here as an exponent. Then the log would be, once again, it would be isolated. But moving that 2 would be a step, and then you'd still have to cancel that 2. So it's like, why? I'm going to go ahead and just divide by 2. And I get x over 2 equals log of y minus 4. Let's cancel that logarithm with a base of 10. And add 4 to both sides. Please don't call that 14, by the way. You're going to hurt me if you do. And I'll go ahead and replace y with b inverse again. And I get my answer, 10 to the power of x over 4. Not 4, excuse me. Why did I think it was a 4? Oh, because I just added 4. See how easy it is to make a mistake like that. Yeah, I had 4 on my mind, so I wrote 4 instead of 2. Just be very, very, very careful with your, ways of writing things. I'm gonna go ahead and call that 10 to the power of x over 2, all plus 4. Do note that because this is a base with a fractional exponent, you could totally call this the square root of 10 to the power of x, or you could even call it 10 to the power of x and then the square root of that. They're all the same, but this is also a perfectly acceptable answer unless otherwise stated. If the problem says, I don't want this with a fractional exponent, then obviously don't leave it like that, but it doesn't say anything like that. So moving on to our final question, number 29, at long last. Let's go ahead and swap locations. Ooh, this one's a doozy just to write out. And you kind of see why people will swap the function notation just for y, just to save strokes of the pen, honestly. So anyways, let's go ahead and try it out. Isolate this logarithm by multiplying by 4, cancel this division of 4. And get rid of the logarithm again, just like we've done with a base. In this case, base 3. Let's get rid of that minus 5, but let's be careful when we do. Well, first of all, let's be careful not to call that negative 2. No, it is not 3 minus 5. Don't call it that. I'm confident that you guys won't, but just in case, I wanted to mention it. And the other thing I wanted to mention was it's a very, very common mistake to forget this minus and just call it C inverse. I'm done. But no, you are not done yet. So let's write this out. You still got to get rid of that negative. So you can do so either by multiplying or dividing by -1, because that's like a -1 times blah, blah, blah. So let's go ahead and divide. Yeah, sure, why not? Let's divide by -1. And I'm going to divide, again, everything on that left-hand side by -1. Now I have C inverse. And dividing 3 to the power of 4x by -1 will give us -3 to the power of 4x. And dividing by -5 by -1 will give us +5. So on the answer key, I actually switched them around. First of all, let me write it how I said it. And on the answer key, again, this is an addition, and additions can be swapped locations. So I called it 5 minus 3 to the power of 4x. And both would be valid. And yeah, there you go. You know what? I think we're done. I hope that was useful. Thank you for watching, and I will see you again next time. Bye-bye.